Do you plan to start doing data analysis and you like to use Spark for it? Have you just started using Spark and you would like to avoid pitfalls? Are you using Spark already and you are not happy about its performance or stability? So here is my promise to you. By the end of the next half an hour, you will have an overview of most common problems faced when running Spark on scale, on production, and solutions for them. My name is Marcin. I'm a data engineer and consultant at Tantus Data. I have almost a decade of experience. I've worked for companies like Spotify, Apple, a few smaller startups. So I have quite broad data experience, and today I'll share the Spark part of it. Apache Spark, if only it worked. It might sound a little bit controversial or provocative, but it's inspired by this blog post. So I found it like a few years ago when I was working with my first Spark application, and the author of this blog post is giving quite a lot of advices, but also he's complaining quite a lot about how hard it is to make Spark scale, how hard it is to make Spark simply work on production. So fortunately, quite a lot has changed since then. So I have learned quite a lot, and Spark significantly improved. And today, I'm not going to put you off from Spark. I'm going to share the lesson learned so it will be easier for you. We will start with introduction to Spark execution model. And this will be our foundation to understand problems you might face and reason about them. Then we will have a look at various classes of problems. So we will be looking at skewed data problems. We will be looking at caching, locality, how to size executors. I'll also say a few words about testing and debugging Spark. So what is Spark? Spark is a general engine for distributed data processing. It has an API for various languages. It has SQL support, streaming module. It has machine learning library on top of it. But for today, we're just going to focus on the core of Spark, which is the distributed data processing engine. So just to give you a very, very simple example of where you can use Spark. So very traditional way of writing applications is that you have multiple applications, they go to database or multiple databases, and then your business wants to know what is going on with your app, what is going on with your users. Why don't they pay? What can we do in order to make them pay for the app? And when analytics are connected to your application database, well, it's not perfect. It's actually risky. They might be too greedy. They might ask too many questions or too heavy questions, and you end up with problems. Of course, you might try to scale it up, but it has limitations. So quite common way of solving this problem is storing the analytics data somewhere completely else. And a very common solution is to use HDFS and then connect Spark to HDFS, so you are doing analysis on top of Hadoop distributed file system. Spark can also connect to multiple other data sources. It can store the result to HDFS or somewhere else, to SQL or NoSQL database, for instance. So let's start with Spark execution model. Spark introduces resilient distributed data sets. So it's an abstraction on top of distributed data set, a data set which is split into a cluster, but when you work with it, it feels like you're working with local collection. And when Spark runs the application, it pipelines operations which can be done on single partitions. So when you run an operation like map or filter, you don't need to collect data from all the partitions, and Spark pipelines those kind of operations. And such group of pipelined operation is called stage. But eventually, you probably want to do something more complex. So for instance, you want to group the data by key. So you have to pull all the same keys into one place. And this is called shuffle. This is quite expensive operation. We will be focusing on that later on. But in general, your Spark application probably consists of multiple stages, multiple shuffles in between. So far, I was just saying Spark does this and that, but the actual execution unit in Spark is task, and task consists of two things: the code, which is supposed to be run, and a piece of data. So if you are reading some data from HDFS, the data is in blocks, so there is single task per each block in HDFS. So your stages consist of multiple independent tasks. Each task gets run in a JVM called Executor. So you control how large the executors are. You control how many cores and how much memory you give to them. There can be multiple tasks run at the same time inside an executor. And I want to emphasize the at the same time, because when task is finished, an executor picks up another task. So an executor is a long-living JVM. You don't have the overhead of creating new JVM per each task, which is quite significant improvement comparing to Hadoop MapReduce. So let's very quickly zoom into shuffle. And you might ask, why do I need to know how it works? Why don't I just rely on the very nice Spark API, and why don't I just let Spark do the job? And the answer is quite simple. So you have to understand what's going on under the hood in order to understand problems you might face and eventually fix them. So task one is processing a single partition, and it's doing operations which can be done in context of this single partition, and eventually it stores the result to local disk. The result gets stored into multiple buckets. Each bucket is responsible for a certain group of keys. And the same happens in all other tasks in stage one. So you have all the buckets stored locally on the disk. And when you do an operation like group by, stage two can pull the same bucket to the same place. So all the red buckets are going to the same place, so you have all the keys together, and you can process it from there. So as you might have noticed, this is quite expensive. It involves a lot of I/O, disk, network. But let's say that's fine for now. But in general, on the slide, it looks OK. So you might ask, what could possibly go wrong? Like famous last sentence. And there are tons of things which can go wrong. So imagine you have your application, you have tested it locally, you are quite confident about its business logic, and then you go to the cluster, you run it all on large data set, and you see one of these problems. So Spark is complaining about 2 gigabytes limit for the colorful bucket I was showing to you. Spark is complaining about some timeouts, some memory problems, or executor lost failure. None of this is really related to your business logic, not directly, so what could have happened? Quite common problem and quite simple to fix is that your tasks are simply processing too much data, so they are choking with the data you process. And so it might choke somewhere inside the task, but it also might choke when it tries to send the data over the network. The buckets are too large, you end up with timeouts or Spark complaining with the 2 gigabytes block limit. So let's have a look at how you can actually investigate these kind of problems. So there is Spark UI for that. and it gives you tons of information, but what I want to focus on is the task overview table. So per each task, you get some metrics, and the ones I would like to focus on are the status of the task. You definitely have to keep an eye on that and investigate the failing ones, but also duration of a task, garbage collection time spent on given task, and amount of memory read and written during the shuffle gives you an overview how heavy the tasks are. And if you can see very long-running tasks, you definitely need to do something with this. So very first thing you could try is to control the level of parallelism. So every single method which is triggering shuffle, like group by, reduce by, has a parameter, num_partition. So you can simply play with this parameter and increase number of partitions, so increase number of tasks. So hopefully each task will be processing less data. That's very simple. Another thing you could try is to simply give more resources to your executors. But obviously you have some physical limitations, and this is not something which scales very well, so this is not a solution for every single problem you might face. So let's see what we have. We have a group by, which is producing just 3 partitions, so 3 tasks, and you want to fix it because it fails for some reason. So we increase number of partitions. You end up with a lot more tasks, but each of them is simply much smaller, so they have no problem with going through. They produce much smaller buckets, so it's much easier to transfer those buckets and so on, and all the downstream stages are lighter as well. And that's very simple. That might help you in tons of situations, but sometimes it's just not enough. So let's say you increased number of partitions multiple times. You end up with a lot of tasks, but still some of the tasks are basically doing nothing, but there is this one which is processing too much data, which is basically still choking with amount of data it has to process. And it's usually caused by skew data. So just to give you an example, if you are grouping your data by country, probably some of your countries are much heavier. Some of your countries has more transactions, more users, and you end up with the very, very large task per specific country. Another example is when you allow your key to be null, and then it happens that half of your keys are null, so you process almost all of the data in one task, and the rest are simply doing nothing. So very simple and general solution for that is adding salt to your keys, adding some randomness to your keys. So you have key foo, which let's say is occurring too often in your data, and you want to split that. So you are adding some randomness to them. You split your keys into multiple buckets. So those new keys are artificial. So you have to keep in mind that after the processing of your data, you have to merge it back together and make sure that your business logic stays correct. But in general, this is how you handle skew data problem. Another very important topic which you definitely want to dig into if you want to benefit from Spark is caching. So I mentioned RDD before, but there is one thing which I haven't told you so far. RDDs are lazily evaluated. So when you calculate the blue one, the RDD one, it doesn't store any intermediate result to disk. It just calculate it on the fly when the data needs to be materialized. So let's say we reuse RDD1, so we do some more operations on the left-hand side, and we store the result to disk, and then we do some other operations on the same RDD1, and again, we store the result to disk. So that's fine, but there is a caveat here. The blue part gets executed twice. So Spark does not store any intermediate result to disk, so it saves you some I/O, but that means some operation you have to execute it twice, and that might make you, I don't know, sad or disappointed. But if you want to avoid that, you have a caching mechanism for that. So Spark can let you cache your data to memory, to disk with replication factor, which means you store it into multiple machines. And also you can do a checkpointing, which is simply caching to HDFS. So every time you can see a branch in your execution plan, it's a candidate for caching. But as you might already notice, your memory is limited. So the question is, what do you cache and how do you cache? And you actually have to be very careful about it, because Spark doesn't let you control priority of your RDDs. So you cannot pin an RDD to memory. And when it's just using LRU algorithm. So whenever you cache an RDD, and then you cache another one, you might lose the one you've already cached. So in order to plan the caching strategy, you definitely need to know roughly how much memory the RDDs will be taking, and you can check that in Spark UI. And also, you have to know how expensive are the RDDs you are caching. So you have to know roughly how much time and how much resources is to calculate the RDDs. So you definitely want to cache the expensive ones. You don't want to risk caching something not that heavy and losing something very important for you. Another thing you probably considering already is, well, if I cannot cache everything to memory, why don't I cache all the RDDs I'm reusing to disk? And it's kind of intuitive, but it's not necessarily a good idea, because sometimes caching data to disk and then reading it back to disk is just heavier than just recalculating the data. So sometimes recalculating an RDD is completely fine, and you simply accept that. One more thing to keep in mind is that all the colorful buckets I was showing you on the shuffle slide, they get persisted and they are kept on the disk so they can be reused. So the recalculation does not happen from the very beginning, it happens from the last shuffle. So I have mentioned executors, and it's very. I got a lot of questions like how you size them. So you can choose from very tiny executors, which and a lot of them on every single node. You can also have very beefy executors, which are occupying most of your node, and you can choose literally anything in between. So the question is, what do you want to choose? It's very dependent on your use case, but things to keep in mind. Spark can benefit from running large executors which are running multiple tasks at the same time. So Spark can share some variables inside one executor, so they are reused by multiple tasks. So this way you can save some memory. But on the other hand, large executors might be simply not granular enough. If you have 100 nodes cluster, you probably don't want 10 very large executors. You probably want to distribute them over the cluster. And also, very large executors are often a cause of garbage collection problems. So very large executors which are processing multiple tasks at a time. You probably need to give a lot of memory to them, but that means the garbage collection might be struggling with large heap. So my recommendations are, if you are processing some ETL data and you're not relying that much on caching, probably starting with 1 up to 4 executors with small ones is good enough. But if you are using caching, or if you plan to use broadcast variables, which we will be talking about, that probably requires you to play with larger executors. Before we go further, I'd like to show you Spark memory model. So you control the size of executor heap. The heap is split into multiple areas. So you have an area for user program, for the memory you are explicitly allocating. You have an area for intermediate buffers used during shuffle, and you have area dedicated for caching. But there is also one more area which is outside of the heap. So this is overhead for a container. And this is used by container, but also it's used for all the off-heap memory you are allocating. So if you're doing that explicitly, or if you are using a library which does so, make sure you make it large enough so you avoid problems. Also, make sure that you are not too greedy. You leave some resources for your operating system. If you are running it on Yarn, let's say, probably your admin already took care of that, but if not, make sure you keep some space for the operating system. Whenever you are not sure about your memory consumption, you can kind of artificially check it. So you can cache an RDD and check the size of it in Spark UI. Spark UI tells you how much given RDD is taking in cache. In some cases, you have a job which sometimes is running on very small data sets, sometimes on very large one. So if you don't want to allocate the whole cluster every time, even if you're running it on small data set, you can try dynamic resource allocation, which is simply Spark taking care of introducing more executors when it sees a lot of pending tasks. Okay, one more concept I would like to show is locality. It's very well known. It's borrowed from Hadoop. So the idea is simply when you process a data, you want to process it close to the data. You don't want to move the data. You want to bring the execution to the data, not the other way around. So if you want to read HDFS block 1, you want to read it on node 1, not somewhere else. And Spark does it for you. Spark takes care of that. But there are certain situations when you struggle with it, and you can be a little bit helpful to Spark. So in some situations, there are not enough executors ready at a given moment to pick up a task in, let's say, node 1. So it gets run somewhere else. But if you want to improve it, you just increase number of executors, and that makes it more likely that there will be executor ready to pick up a block, a task in given locality level. There is Spark locality wait parameter, which tells Spark for how long it should wait for running a task in local mode until it gives up. You can play around with it. You can actually enforce locality or give it up entirely. But also, it's also quite tricky. So you have to really know what you are doing. Join is a very common operation when you write your Spark application, and the way it works is very similar to group by shuffle. So stage 1 is producing all the buckets. Stage 2 is producing them, and when you want to join the result of both stages, they all go to the same place, so all the red buckets can be joined together in stage 3. And as I already mentioned, it's expensive, but fortunately there are scenarios when you can avoid doing shuffle when you join the data. So in this execution plan, stage 1 is doing group by key, and then it's doing some map operation. Then stage 3 is doing group by key and some map operation. But let's say you know that you are not modifying the key in your key value pairs. Let's say you modify just the value and you know about it. The thing is that Spark does not know about it, but you can use map values function to inform Spark about it. And then Spark can use that knowledge to optimize the job. And if at the same time you are using the same number of partitions for both group by keys, that means Spark knows key A from stage 1 is in exactly the same place as key A from stage 3, so it can avoid shuffle. So this execution plan, which contains of 5 stages and 4 shuffles in between, becomes this one. So we have 2 shuffles less. Both group by keys are happening in context of the same task. The map values happens in memory, and the join also happens in memory. So avoiding 2 shuffles is usually quite significant improvement. There is one more way of avoiding shuffling the data in Spark, and it's called broadcast variable. So the idea is that you send given variables, send some data to every single executor, and they are basically stored in each executor's memory. And imagine a situation that you want to join RDD1, which is very large, to small RDD2. So what you would have to do in this case, you would have to shuffle RDD1, an expensive one, shuffle RDD2, which you don't care that much because it's small, and then join it together. But what you can do instead, you could broadcast the small one, so RDD2 is in memory of every single executor, and then the join can happen on the level of each RDD1 partition. So the join can happen in context of just single node. You don't have to shuffle RDD1 at all. I want to mention a few words about running Spark locally and testing it locally, and there will be actually a very quick demo of doing that. So you can run Spark locally, and it's super useful for learning, but also it's super useful for making sure you are testing your code in local mode. And testing your code in local mode is not only about quality, it's also about how fast you can iterate. It's simply much faster to test things locally rather than going to the cluster, waiting for resources, than waiting until the job is finished and then maybe investigating some large amount of data. So it's very useful for testing, and it's also very useful for debugging in certain scenarios. So I'll show you a very quick demo. So the use case is that we have a directory with tons of CSV files, and we are simply interested in just some of the columns. So we want to output new CSV with maybe some UUID, which will be a key for further processing, or maybe a key for loading the data into a database. And let's say you observe that increasing number of CPUs per executor didn't bring you any benefit. So you increased it from 1 to 4, and you expected roughly 4 times better performance, but nothing has happened. So you could investigate it on the cluster. You have some suspicion, so maybe you could connect to the cluster processes. But what you can do, you can run it on local mode. So this is the solution of this problem. There is tons of like boilerplate code. We are telling Spark to run in local mode, which means there will be a single JVM running 4 separate threads, each running a task. So we are simulating a single executor with 4 tasks. And then the actual solution, so we calling a map with this function. So we parse a value and we output UUID, first column we are interested in, and the second column we are interested in. And this will be run in parallel. And we can actually attach a profiler to that, unless some of you already see what the problem is. So we have a lot of these red blocks, which means that a thread is blocked. And I can tell you that this is not really directly related to Spark. So we have multiple threads which are run in parallel. So do you see what is wrong with this code? Okay, so if you actually have a look at random UUID method, it's simply using a synchronized code. So when you run it in context of the same JVM, it basically blocks itself. So what you could do, you could use some other UUID generator which is not blocking. I decided to use the one from Spring just for the sake of the presentation, and we had to do one more change because that one is also blocking when you instantiate that. So you have to make sure you instantiate it just once, and then you iterate over the whole partition and reuse the generator. But simply when we run that, what happened? Everything is green, and you can observe improvement in the time of execution. So I understand this is like very specific example, but the point is that running Spark locally can actually help you investigate certain groups of problems, and it's simply you don't have to go to the cluster, you don't have to install profiler on every single node and so on. Okay, so some general notes at the end. Make sure you test your code, and once again, it's not about quality only, it's also about how fast you can iterate. It's very hard to investigate distributed systems like Spark. So the more you can do locally, the better. Make sure you know what you are optimizing for. So you might optimize for wall clock time. You might optimize for resources. You you also, it also might be that your time is too precious to rabbit hole on some small problems. So make sure you know what you're optimizing for and do it in a sane way. Keep in mind that you are not the only user of the cluster, most likely. Most likely you have tens or maybe hundreds of users of the cluster, and make sure the changes you are doing, the optimizations you are doing, if you are, let's say, too greedy with resources, you are blocking with other people, and it might be that your job is not the most important one in the company. Make sure you come up with some guidelines. So it's very common that there are developers, there are admins, but also there are people who are interested in running SQL from time to time, and they are not that much into what's going on in the JVM, what's going on in Shuffle, but make sure you make some guidelines so you don't really have to investigate the same problems all over again each time. And the last comment is somehow related to the title. Spark actually works. It just helps a lot to understand what's going on under the hood. And the more you know, the more you work with it, the nicer it is. Thank you very much. There will be, I think, plenty of time for questions. So you can ask them now. You can ask them later on if you have some more specific use case to discuss. And yeah, get in touch if you are interested in training services or consulting services. So. So it really depends. So the question was whether in projects I've worked, I had to maintain old-fashioned relational databases. So, sorry, data warehouses. So it really, I would say the long-term solution should be getting rid of that. So one of the projects I was helping with was simply getting away from huge MySQL clusters because all the analytics and all the applications were using like huge MySQL clusters. So doing such kind of analysis can definitely get you away from old-fashioned data warehouses. And I would say that should be a long-term goal. Anyone else? All right, thank you.